Hello, Garg sir. Yes. Yes. Can we start, sir? Hello, sir.
Hello.
Can we start now?
Yes, yes. Am I
Yes,
audible?
thank you. Good afternoon, everyone. Yeah. Yes.
Do you want me to start my video also? I mean, I cannot see the video option here.
Okay.
Okay.
Yes. Can we start now?
Yes.
Thank you. Good afternoon, everyone. Honorable Director General Sir, Honorable Director Madam, and dear participants, we are privileged to have a renowned personality, Dr. Madhukar Garg, President of Refining and Petrochemicals R&D from Reliance Industries Limited with us as a resource person for today's session in this faculty development program. It is a great honor for me to welcome and introduce Dr. Madhukar Garg, sir, on this occasion. Dr. Madhukar Garg is an acknowledged expert in petroleum refining and petrochemicals and has been instrumental in developing and commercializing large number of technologies in the Indian refineries. A graduate from Nagpur University and a postgraduate from IIT Kanpur, he did his PhD with Professor H.R.C. Pratt at University of Melbourne in solvent extraction. He served Engineers India Limited in the Research and Development Center for 18 years until 1994 and then Technif ATI for 4 years before joining CSIR, Indian Institute of Petroleum in 1998. He has been the director of the Indian Institute of Petroleum for 13 years from 2003 to 2016 and officiated as a Director General of CSIR during the year 2015. His areas of specialization include solvent extraction, process integration, advanced control, simulation and modeling, besides the ability to conceive research ideas and take them to commercialization. He has won several awards. Some of most prestigious are MOPNG, that is Ministry of Petroleum and Natural Gas Innovation Award 2016, TDB, that is the Technology Government Board's Technology Day Award 2017 and 2019, ICC, that is Indian Chemical Council's Lifetime Achievement Award 2013, Wasvik Award 2017, besides several CSIR technology as well as innovation awards from 1998 to 2016. He has published more than 300 papers in refereed journals and is the inventor in 44 national and 22 international patents. He is the elected fellow of the Indian National Academy of Engineers. Currently, he is president of Refining and Petrochemicals R&D of Reliance Industries Limited. Now I invite Dr. Garg to take the floor. Please, sir.
Thank you, Nitin, and thanks for such a generous introduction of mine. I think it's both a pleasure and an honor to address the faculty in this very important program, what you call as a faculty development program.
Yeah.
As you know, education is always a continuing process, all the way from birth to grave. And it's more important for the faculty to continuously upgrade their skills in order to prepare the future generation of engineers and, more importantly, chemical engineers to serve our industry better. Talking about industry, of course, from my short biodata, you must have realized that most of my time I've actually spent in the industry, as I do even now. And therefore, I chose a topic which is a cross link between academia and industry. Most of the faculty members in chemical engineering, they do teach process control. And therefore, I thought it would be a good idea to talk about what we practice in the industry in terms of what is called as advanced process control. And when I say industry, I think primarily I'll be kind of referring to mostly refining and petrochemical industry, because that's where I have spent more than 44 years of my career. But nonetheless, the reference to this industry doesn't mean that these ideas and concepts can be applied only to petrochemical industry. It can be applied to any other industry. And as I was mentioning to Nitin yesterday, that some of the ideas that I'm going to talk about can very well be implemented by the faculty of MGMCET in small and medium scale industries, which are abundant in and around Mumbai, Maharashtra, and Gujarat. So let me actually begin, and like to also add that although we might have questions at the end of the lecture, but in case somebody is not able to understand a certain concept, feel free to actually stop me so that I can explain that before I go forward. Uh, I will try to make it as interesting as possible. I know it's after lunch and it's perhaps the last lecture of this faculty development program. So people get saturated after so many lectures and they feel that why another lecture, right? I would feel exactly the same way as you would do. But believe me, this is something that will actually stay on for the rest of your lives in terms of what you can do. And it's very easy. I'm not actually made it very complicated for you to understand. Okay, as we go forward, I'm not able to move. Nitin, I'm not able to move my slides actually. Here we go. So I think, as you know, with the current times that we are going through, where actually the refinery margins and in general, the profit margins in any industry has come down, not only because of the epidemic that we are going through, but also actually in usual times, making money is always a challenge. And therefore, the industry looks for quite a few alternatives. I'll actually try to use a laser pointer. Generally, of course, a good thumb rule is to do general housekeeping so that we don't have leaking steam traps. We don't have, big, what you call, flames, and so on and so forth. So I think this is something that the industry does in terms of making sure that there is no leakages, etc. On the other hand, the other approach to make improvement is to actually retrofit the current units with a better catalyst, with a better solvent. If there's a distillation column with a better internal, because as you know, technology keeps on changing as we speak, and therefore it's very important to actually continue the development to keep track of the development and to retrofit and introduce new ideas into our current operation to maximize profit and thereby become more competitive in the market. Whether we actually do general housekeeping to the best extent possible or we do a new design, it's extremely important that we also look at a third angle, and that is to actually maximize the return out of our existing assets. And it is also called as sweating of assets, where with the current capital that we have invested, we would like to make the maximum money out of it. And one of the enabling tools to make it happen is advanced control. And the benefits are smaller, but of course the investment is also smaller. And although the benefits would be of the order of 5%, but the payback is hardly ever more than 6 months. So it's a very attractive option in the hands of the companies to actually look at advanced control more as a habit and as a part of the system rather than some new experiment that they would like to do. Why it is important to talk about control and advanced control? If you look at this chart, what I have plotted here is the process value and set point of a particular variable with respect to time. And if you don't have a very tight control of the process, and what I mean by control, it's basically, as you know, control of pressure, temperature, level, and flows in a process unit. So if you don't have very tight control, actually the process variable wavers around the set point quite a bit. And some of the times it might actually violate the max limit as well. Now, when it violates the max limit, that means the product becomes a little impure. It might have some impurity. Like, for example, if you're trying to separate benzene and toluene, and the benzene purity, as you know, in the merchant market is about 99.995% pure. So any amount of small toluene ingress in that would actually make that product unmarketable. So what generally the operator does is that he tries to keep the set point pretty low as compared to the actual value. And therefore, actually, he is quite happy to let some benzene go along with the toluene. So that's a kind of a loss in production. And that can be avoided by raising the set point if we have a better control. So as compared to the previous chart where the process variable actually wandered quite a bit around the set point, in this case it is tightly around the set point, and as a result you can go all the way from 40, something like 50 to a value of 55 in terms of set point, and therefore actually and be still lower than the limit, so that you never violate that limit, and also you have a higher production, and therefore you make more money. So when I talk about control and advanced control, this is not just a theory. It is actually something which is in practice, and more importantly, it gives money. And at the end of the lecture, I will teach you how to actually calculate benefits of advanced control even before implementing advanced control. Actually, the management generally before they approve a project, they always like to have an estimate about what is the cost benefit ratio. In other words, what will be the capex and what will be the EBITDA and what is the capex upon EBITDA. So that actually gives them the idea about rate of return and net present value. So that cannot be done unless it is implemented. But the good news here is that you can actually calculate estimates before implementing advanced control. And I'll talk about it later on. Now, no discussion on advanced control can ever be successful unless and until we talk about the instrumentation in the control room. As we talk today, because of digitalization right across the entire economy, and even today as I speak, it is because of digital enablement. Today, actually, all the control rooms in almost all industries, whether it is fine chemicals, pharma, and more importantly in refining and petrochemicals, is provided with DCS, what is called as a distributed control system. But this has actually evolved over a period of time. And if you look at the control room instrumentation, the way it has actually evolved, up to 70s, you'll be quite surprised to know that all the instrumentation in the control room was mostly pneumatic, and it was on the wall, panel mounted. So all these control rooms had a big wall on which the entire semi-graphics of the unit was displayed. And all the PID controllers were pneumatic in the sense that the signal coming from the plant was in terms of a pneumatic air pressure signal. And that was compared with the set point, and what the signal went out was also in terms of pneumatic air pressure. And I have actually, I'm kind of old enough to actually see this happening. Most of the refineries actually till 70s or even late 70s had a pneumatic control panel mounted system, and I've even operated some of the plants using pneumatic control system. In early 80s, once electronics actually started to come in, as most of you may not even know, that the first calculator that I have used and which actually became available to engineers was way back in 1976-77. In fact, my engineering, I had no calculator. I had to use slide rule and log table. But 76, 77 calculators started to come in, which could do only 4 functions, plus, minus, division, and multiplication. But there was some element of electronics which started to creep in, and that was actually taken in full glory by the industry, which converted the pneumatic control system to electronic analog. And then with digital electronics coming up in mid 80s, this were converted to what is called as SLPC, that is the single loop programmable controllers. The single loop programmable controllers actually had the PID algorithm, which was engraved in the chip in the single loop programmable controller. So the operator gave the set point, the process value, either temperature, pressure, level, or flow, came from the plant in terms of a digital signal that is 4 to 20 milliamp, and that was compared, and an electronic signal was sent back. Yeah, Sanjay, you had to ask something? Somebody has raised a hand. Am I audible?
Yeah, you are audible. Sir, the questions we will take later. So I think
Right.
we can continue.
So, and then after mid 80s and beyond, the single loop programmable controllers gave away to what we today call as DCS, which is called distributed control system. And so slowly the industry actually upgraded their control system from pneumatic, but it was not in one step to go from pneumatic to DCS. It went in steps like pneumatic to SLPC, which was single loop programmable controller, still panel mounted. And the operator still actually walked across the wall to note down all the data, which he was very used to. So there was, basically the idea was not to give a kind of a cultural shock to the operator and actually maintain roughly the same way and give him the same look and feel. Then later on, as new generation of operators started to come in, DCS was added to the SLPC, and today as I speak, we have DCS. So how it went about is that this is the field. This is where actually this field is nothing but the plant. It could be any plant. It could be a crude unit, vacuum unit, FCC, naphtha cracker, anything. So from the field, you have 4 types of signals. That is the flow, pressure, level, and temperature, which come in. And there are 2 types of control system that we have in the control room instrumentation. One is we call as an open loop, where the flow, level, pressure, and temperature are only indicated or recorded for the information of the operator. The second is the closed loop, where these signals come in and they are compared with the set point, and the deviation or manipulated variable is sent back to the plant to operate a control valve. So I repeat, the control room instrumentation is either open loop like this one or closed loop. Now this was actually the panel mounted, the first upgrade. Then later on, this was combined along with the DCS, what we call as operating station. The operating station is very similar to a computer, the desktop computer that you see. There's no difference between that and a desktop computer. The only thing is that rather than a simple PC, it is actually a workstation. Most of these are actually HP workstations, which are tremendous amount of computing horsepower. And actually feeding to these operating stations is what is called as a control station and monitoring stations. The difference between these 2 stations is that the monitoring station takes the open loop signal. So in addition to the flow, level, pressure, and temperature, which are in open loop, going onto the panel, they are also fed into this monitoring station. And the monitoring station in turn actually feeds its data to the various operating stations. And sitting in front of these operating stations are the operators who actually look at this data in a form of in various formats that it is displayed to them to help them to control the plant and operate the plant better. The closed loop is actually piped through the SLPCs, into the control station. This control station is actually containing the PID controller also. So to some extent, there is a redundancy that is provided. So in case the control station goes down, the operator can still operate the plant through the SLPC. And then that also feeds to the operating station. This went on for quite a while. In fact, some of the refineries, including the two here in Mumbai, the Bharat Petroleum and HPCL Mumbai, still have configuration something like this. But slowly, they have also moved that to something like in this picture, where there is no longer panel mounted instrumentation anymore. The data is from the plant is fed directly to the two stations, the control station and the monitoring station, as I showed you earlier, without the middle layer. And then that data is then sent to the operating station, and then you can add other modules like an application module or a supervisory computer to that. In fact, the control station now takes more responsibility, because in case it goes out of order, there is nothing to fall back upon. And therefore, what we do is we provide a duplex control station, that is two CPUs in parallel. So in case one CPU goes down, the second takes over, and there's a hot data transfer between the two. So the redundancy, the availability, on-time availability of the current DCS is measured in the fourth and fifth decimal in terms of 99.99995%. So the reason is that we can't really afford for any of it to blank out, because then the operator has no other way to know how to operate the plant, and the plant can get into a dangerous situation. So this is what is important for you to remember, that if distributed control system would not have been invented, there can be no discussion about advanced control, because the advanced control comes and sits on these operating stations and control stations in this picture. What is the benefit of digital control, the way we saw it? Of course, it has enhanced data accuracy, because now you have much more accurate data in real time. So if the temperature is 98.5, it will show 98.5. In good old days, the operator guessed it was somewhere between 96 to 99. So that was, the data accuracy has improved. Very fast response time, because we're looking at electronic transmission here from the plant to the control room and vice versa. A very easy access to plant data. You can actually record and store data for the last 10 years. And the way you actually recall your files on your laptop or computer, you can recall these files as well. So there is no need to actually keep track of ledgers and folders, hard copies anywhere. This is all available electronically. More important is that this particular media provides you facilities for plotting, trending, and even storing process data. So if you want to determine the effect of one variable on the other, you can actually transport the data into the Excel and plot and trend it, or even you can do the plotting trending on DCS. To my mind, the most important advantage of digital control is that ease of control of configuration and tuning. What I mean by here is that the plant is never steady. Over a period of time, it goes through revamps, it goes through modifications, etc. And one of the modifications which is generally done is that we change the control system. Like, for example, if I'm controlling the reflux, manipulating reflux based on top temperature control in the distillation column, at some time, some bright guy from the technical services might feel that the tray 5 temperature might be a better variable to do an optimum reflux control. So he might like to take there would be an indication for tray 5 temperature, but then this configuration has not been provided by the licensor. Now, in good old days, it was next to impossible to do that, because there were hard lines going up and down. There were actually pipes going up and down, but here it is electronic signal and everything is available on the DCS. So it is just a matter of few minutes that he can actually change the controller configuration. All this is hunky and dory. Everything is great. But the bad news is that the underlying control philosophy still remains the same as before. Although, we have tremendous horsepower computing, computing horsepower here. But the good old controls, algorithm remains the same. And what is that? That is something that you all know. It is the age-old PID controller. And PID, as you all know, stands for Proportional Integral Derivative Controller. Since you all know about it, I will not explain, but let me actually tell you some of the major features of a PID controller. You have actually a process, which is an inherent part which you want to control. And let's say actually you want to control, and this is the pipe. So this pipe is a process where you want to control the flow through this pipe. So what you do is that you have a measuring element, which could be an orifice plate or something, which measures the flow of this fluid, and that is the present variable. The PV value is the present variable or present value, and it goes into the controller, which is the PID controller. And the PID controller compares the PV value with the set point, which is given by the operator, and it actually then uses the algorithm, which is the PID algorithm. I don't think we have the time, and neither is the forum to discuss what is a PID algorithm, but it actually uses that algorithm to calculate the manipulated variable move, which actually is downloaded onto the control valve, and the control valve opens or closes accordingly. So if suppose the flow is higher than the set point, then this control valve will close and vice versa. So this is what is called as a conventional single loop control, and it has been around since time immemorial. In fact, whenever the first plant was constructed, PID controller has been there. In fact, PID controller is the major workhorse of anything which moves, whether it is the plant, whether it is a ship, even whether it's an aeroplane. So the PID controller is a workhorse. Having said that, so if it's such a trusted controller and such a trusted servant, what is wrong with it? What is wrong is that there are certain limitations of this conventional PID control. As I said before, this variable should be measurable. So we are left with only 4 variables that we can think of: pressure, temperature, level, and flow. If suppose I have a problem in terms of controlling the flooding in a distillation column, or if I have a problem in terms of making sure that the horsepower of the compressor doesn't exceed a certain value, etc., etc., I do not know because I can't measure that. Or even actually, if suppose I'm making a product of high purity, like propylene, to make polymer grade propylene, and the propylene quality should be 99.95% pure. I don't have, unless I put a online gas chromatograph, I have no idea as to what is the purity. So control variable should be measurable. That is the first limitation. Second is the disturbance must affect the process first. In this case, it's a feedback loop, as you know. So the measuring element should show a higher flow, and only then this controller will take action to reduce the valve opening to reduce the flow. So disturbance must affect the process first, and many cases, this is not a desirable thing, particularly when you have very heavy duty furnaces, etc., where actually it could affect the metallurgy of the pipes and the tubes. Limits, constraints cannot be handled. For example, if suppose I say the process variable here is very low, and as compared to the set point, and the signal by the PID controller is to open the valve. Now, if I open the valve and continuously open the valve, the PV value still doesn't get to the set point, and the valve is fully open. So this controller doesn't know that there is a certain limit beyond which he cannot open the control valve. So such limit constraints cannot be handled. If there are significant time delays in either measurements or process response, it destabilizes the loop. In other words, if suppose I have an online gas chromatograph, by the time the sample T goes into the coil and into the column, and by the time it actually enters the detector and the signal comes back, there could be a significant time delay. Now that is something that time cannot be actually considered. It cannot be handled by a PID controller. The other aspect is that it cannot handle interaction with other loops. So it knows only its own process variable, its own set point, and its own manipulated variable. It doesn't know what other loops are doing, and obviously the plant is integrated. So any action by any other loop will affect this loop as well. So that's a big constraint, and therefore, and as you know, inherently, there's only one control algorithm per loop. So tomorrow, if suppose I want to change the gain value, or if I want to make sure that the PID controller doesn't operate for some reason, those kinds of algorithms cannot be actually built into this. So it will only operate at one algorithm at a time. So given all these constraints and knowing that the PID controller is a faithful workhorse, what is the next logical step that we should do? So obviously, since there is tremendous computing horsepower available in the DCS, the existing features can be used for control beyond conventional control, and that is called advanced control. So anything beyond PID controller, even a ratio controller, is called advanced control. And it helps to eliminate the drawbacks of conventional control. Not only that, it helps you to make money. And as I mentioned before, I will tell you how you can calculate benefits due to advanced control. And in many cases, in almost all the cases, you can estimate the advantage of advanced control even before implementing advanced control. Let me give you an industry scenario as to why advanced control is required and is a must in the industry today. See, for example, even if you employ the most sincere operator, he will make adjustment 5 to 8 times per shift. Okay, so even if he's very dedicated and sincere and very knowledgeable, it's very difficult for him to make more than 5 to 8 adjustments per shift in one parameter as what he thinks is the best. So this is again underlined as per his perception. And this kind of an adjustment can vary from person to person. Obviously, there are 3 shifts in a day, so there are 3 different people in a 24-hour in a 24-hour time frame. So from one shift to the other, the situation can change, and therefore, actually, you need something which is more consistent. So advanced process control fills that gap because it can adjust multiple parameters, not one at a time, but it can adjust multiple parameters every minute as per the agreed objectives to maximize productivity and profit. And what's important is that it is independent of the person. So whoever is the person sitting on the panel to operate the plant, it doesn't really matter because advanced process control based on the objectives which have been decided by the higher management will always drive the plant to its maximum profit objective. So this is something that this cartoon tells you the whole thing very succinctly. So here, this is the lab person. Actually, he reads out the data in terms of Kero ASTM. Kero is kerosene. And kerosene 95% boiling point is an estimate that these guys do in the lab by running a simple distillation column called D86. And this data is actually relayed by him by I've seen this these times. Now, of course, we have LIMS and other software wherein he types in the data and it goes automatically to the DCS. But in those days, actually, he used to pick up a phone and call. And the operator will write it in a register and a book, which is a huge book. In fact, the weight itself of that book was huge. It was very long book. It used to be called as a long book. And there actually the data was entered. And then based on that data and what exactly the company wanted, the operator used to adjust operating conditions in the plant and then wait for 8 hours before the result was affected. I mean, the change made any difference, and then take a sample and send back to the plant. And the loop closed. But today it's not exactly the same. Today, the Kero 95% point can be actually estimated. It cannot be measured. There is no measurement device by which you can actually measure 95% point of Kero, but it can be calculated online, and that can be displayed to the operator. And based on that, he can adjust the kerosene flow out every once in a minute. And this whole loop of having a lab, etc., is completely eliminated. This is actually what I call as digitization in the real world in terms of optimal operation. Now, before I get on to the nitty-gritties of telling you, so I've discussed why, but now I'm getting to the what. And later on, I'll talk about how. If you remember, there was a slide where we said what, why, and how. I think very important is why, and I hope I've convinced most of you that advanced control is a necessity rather than a fashion. And after convincing you upon why, then we talk about what, and then how. Actually, this graph is clearly my thought process. In fact, you'll never find this in any book or literature. But having implemented advanced control in 6 refineries and petrochemical complexes during my tenure in Engineers India Limited, what I feel is that any process control, which is actually control of these 4 variables called temperature, pressure, level, and flow, is nothing but actually control of the chemical engineering part of the process. So when you are actually operating a distillation column and you're trying to control the overhead temperature, the pressure, etc., what exactly you're trying to control is one or more of the chemical engineering operations in the plant. It could be either a mass balance, it could be either a heat balance, it could be reaction kinetics or reaction engineering, or vapor liquid equilibrium, or a combination of them. So it could be either thermodynamics or catalysis or kinetic reaction kinetics, heat balance or a mass balance. And these are all the subjects that we teach and we learn. And this is actually what defines chemical engineering in to a very large extent. So please always remember that whenever we try to control these 4 variables, we are actually trying to understand the chemical engineering background in that process and trying to control that part. And having understood that, now let me tell you what is advanced control. Advanced control actually comes in multiple layers. And like right at the bottom is the PID control system, the regulatory control system that we talked about. That is a single loop control. And then above that is the advanced control system. And I'll talk about that in a greater detail during my presentation. Advanced control comes in different flavors, and I'll talk about that in a moment. But the advanced control layer, what I would like you to remember is that this advanced control layer sits on the top of the PID control. It doesn't actually substitute that. It's very important. So we do actually respect and honor our good old working horse, the PID controller. We don't ever allow any control system to bypass the PID controller. But now the set point to that PID controller is being given by the advanced control system rather than by the operator. Okay. And over and above that could be a unit optimizer, where actually, in addition to advanced control in the unit, you would have an online optimizer, which is something like optimizing the process at a steady state. So it looks at various other, parameters like profit and utilities and so on and so forth, and decides what could be the way this plant should be operated. And it actually takes it from one operating window to the other. So the unit optimizer downloads the set points, if I might say so, on the advanced control system and tells advanced control system that this is the way you should operate the plant. And then advanced control by itself has its own algorithm to download the set point of the pressure, temperature, level, and flow values to the regulatory system. You could even have further layers like multi-unit optimization, where, for example, if you have a reformer, and as you know, reformer is fed by a naphtha hydrotreater, and before the naphtha hydrotreater, you have a naphtha splitter. So you got 3 processes in series. So you got full range naphtha coming in, and you got light naphtha being split, and the heavy naphtha goes into a naphtha hydrotreater followed by reformer. Now you could actually do a unit optimization on the reformer, just the reformer part, but you could do multi-unit optimization, including the naphtha splitter. So basically, based on the naphtha composition, the naphtha splitter optimization would actually get you the major precursors in the feed required for you to make aromatics. And over and above, it could be planning and scheduling, where actually this looks at a larger picture in terms of what crude is coming in, and what is its quality, what is the assay, and then you have an LP kind of a program running in, not on a daily, not on an hourly basis, but maybe on a daily basis, to actually tell the multi-unit optimizer that this is the way you should be now looking at the operation because the crude has changed. So, like the regulatory control system, there is also a kind of a difference on the time execution. Like the regulatory control system in the current DCS, like the PID algorithm, executes once in 250 milliseconds. The advanced control would execute once in a minute. The unit optimizer might actually execute once in 4 hours or maybe once in a shift. Multi-unit optimization could be once in 2 shifts or once in a day. And the same thing with planning and scheduling. So this is how actually you have multiple layers, depending upon the complexity of the plant and the urge to make more money. One could invest, in some of these layers. And it is not necessary that all these layers might be in closed loop, like planning and scheduling can be offline, and the data can be then actually transmitted through an electronic movement system by which the multi-unit optimization can take through. So here actually there could be a human interface where the people can look at what the planners and schedulers are telling you to do and use their own judgment, because you know the real story about the current plant. Now, this is how actually advanced control is built up in many manufacturing plants. Now, coming to what exactly is advanced control? Okay, advanced control actually has 4 components. It has hardware, firmware, software, and humanware. The hardware is very simple. It is the DCS that we discussed in great length. Then we have the firmware, that is the operating system which operates the DCS. So it could be either Microsoft Windows or it could be Unix. Generally, actually, if you have an HP workstation, um, if you have HP workstation, you would actually try to use a Unix operating system. And then you have a software. So basically, advanced control is nothing but the software, which actually sits on the firmware, which operates the hardware. But in addition to these three, the most important aspect amongst, to my mind, in over and above software, firmware, and hardware is the humanware. That means the people who actually implement advanced control. Let me tell you, friends, that if suppose an advanced control project is about a crore, okay, suppose suppose the company has to invest 1 crore, almost 600,000. Suppose let me talk $1 million. Then almost $600,000 is actually in terms of man-hour cost. Software is only a license of the advanced control software, and if you're good in negotiating, you might even get a site-wide license for a song. Hardware and firmware is your own investment. That is actually, a kind of hardware that you actually buy, so it's your property. Software which sits on that, and software is something which is like your Microsoft Word or Excel or even Aspen or something like that. But the people who actually program this to understand your plant, to be able to understand how the plant operates, and I can actually speak for 3 hours on this particular aspect, because I've seen how control systems actually succeed and fail just because you didn't have the right kind of people. And what I mean by the right kind of people is that the person who implements advanced control should be a multi-skilled person. In other words, he should be a pretty good expert of the process on which he is going to implement advanced control. More importantly, he should have some design knowledge. I mean, he should have at least at some time during his career involved in the design of the unit, so he would understand the entire nitty-gritty of that unit. He should be actually pretty hands-on in terms of the operations of that unit. Given the situation, if suppose the operator is not there, he should actually have the flair to operate the unit himself. Number three is that he should actually have a good experience on statistics and mathematical modeling, because a large amount of effort is required to model the process, and I'll talk about that in greater detail later. And last but not the least is that he should be a politician. Why I say that he should be a politician is that he should be able to integrate the views all the way from top management to the operator. Because in an actual operating plant, the operator has always different views as compared to his boss, and then the technical services sing a completely different song, and they're always actually at daggers drawn. I mean, they don't like. I mean, they may like each other personally. Sometimes they don't even like each other views. So if you have to make it successful, you have to carry everybody and to be able to understand the views of everybody. So I cannot go for too long, but just to tell you that the human aspect, that the manpower aspect of implementing advanced control is perhaps 10 times more important as compared to the advanced control software itself. Now, advanced control actually consists of three very important layers. One is what is called as a conventional advanced regulatory control. So it is a bit more advanced than the PID control that we talked about. It is advanced regulatory control. Generally, this layer is not required, friends, nowadays. People go directly to multivariable advanced control. But why I have kept here in this lecture today is that I would like to talk about three conventional advanced regulatory controls in order to give you a flavor as to where, to give you a flavor and an appreciation of what exactly multivariable advanced control does. And then, of course, online optimizer, as I showed you in this picture, this unit optimization. Today, of course, we'll have time enough to talk about conventional advanced regulatory control and multivariable advanced control at some stage in the future. I can talk about online optimization as well. So let's begin. So now we are talking about going from what to how. So we have discussed why, we have now discussed what, and now we are going to talk about how. The how part is the conventional advanced control, as I said before, and that is part of the total advanced control components that I talked about. There are three concepts which I would like to introduce you. One is called as a nonlinear PID, nonlinear proportional integral derivative controller. The second is the feed-forward control, and the third is what is called as an inferential control. And when I say that, today we only implement advanced control, multivariable advanced control, what I mean is that all these three concepts are actually inbuilt into this multivariable advanced control. And therefore, for you to understand and appreciate multivariable advanced control, it is important to understand what these three are. They are actually the foundation of multivariable advanced control. Let's talk about nonlinear PID control. It's generally used for level control. So let me give you a situation. Let's say you have three components in the feed. I know this is a virtual class. If suppose you would have an actual class, I could have stood on the board and drawn a diagram, which I always do when I give this lecture at this moment in time. But let's say you have three components, benzene, toluene, and xylene, which you need to separate in two distillation columns. So in the first distillation column, you take the benzene to the top, and then the toluene and xylene go to the second column from the first column bottom. And the second column actually distills out the toluene from the top, and you got xylene coming down from the bottom of the second column. Now, if you look at the level control of the first column, what is happening is that since the level is cascaded onto the flow on the bottom of the column, that the bottom stream of the column, which actually goes as a feed to the second column. Since it's a tight level control, and suppose the set point is 50%, if the level goes for some reason to 55%, it will start reducing the flow, and vice versa. That is fine as far as the first column is concerned. But if you look at the second column, that second column gets disturbed. So because of this level controller, so the level controller is continuously changing the feed to the second column, and the second column gets disturbed all the time, and that's the reason why actually, as you know, if you remember, in mass transfer course we teach McCabe-Thiele diagram. So if you relate McCabe-Thiele diagram to this, what it means is that we cannot keep R by F constant all the time. That is the reflux to feed ratio constant all the time. Because if the feed increases, by that time the overhead of the column, of the second column, senses it and starts increasing the reflux, the feed has gone down again. So what I mean to say is that the level in the first column variation actually makes the second column dance. And so if you actually put a nonlinear PID control on the level of the first column, it helps to stabilize the downstream column, and it also is an effective use of the surge capacity. What I mean here is that if you can actually So this is, this is how you show the PID. So let's say this is the gain of the PID controller. And between 20% to 80% level, we try to reduce the gain. So as you know, the PID controller in the algorithm, you have gain open bracket 1 plus 1 upon tau I integral d epsilon by dt plus tau d into dE by dt, d epsilon by dt, where epsilon is the error between PV and SV. So what happens here is that we, by reducing the gain, in other words, we are actually detuning the controller. So between 20% and 80%, it will not take any aggressive action to open the valve. But above 80%, the slope of this line goes up. That means the gain goes up, and therefore it will take more aggressive action because it might actually flood the tray above. Or below 20%, you can take even more aggressive action because we don't want the level to go down too much. Otherwise, it might lead to cavitation of the pump at the bottom of the column. So, and in many cases, actually, you can even make the gain 0 during 20 and 80. So what happens is that the level is at 50, let it keep on going to 55, 56, 58, 70, and we still don't change the flow coming out of the bottom of the column. So that we are using the surge capacity at the column bottom. And actually, believe me, the operators which are very smart, they actually do that. And many times when I sit on the panel in control rooms, I found that many of the controllers, many of the level controllers at the bottom of the distillation column are taken on manual by the operator. And so he actually, about taking on manual means the closed loop control is no longer there. So in other words, he's just trying to control the valve position so that the flow remains constant. So this is in essence a nonlinear PID control, and this is very handy in many applications. The second advanced regulatory control is a feed-forward control. So this is actually, as you would remember from your process control course, this is the set point, and this is the process variable coming in. So you got you take the difference between the set point and the PV and the error, which I mentioned epsilon in the PID algorithm, which I mentioned earlier. That error actually goes into the PID algorithm, and what comes out is the manipulated variable. Now, this is actually added or subtracted from the signal coming from the disturbance. So this is what is called as a feed-forward control. So if you know that there's a measured if there's a disturbance and you can measure it, then you can you predict the impact of that disturbance on the process, and you can actually compensate for that disturbance on that manipulated variable move, so that the process doesn't get disturbed because of this disturbance. Let me give you an example. Just visualize a furnace which is heating a fluid. It could be crude oil, it could be anything. Okay, and so basically what you do is in such a system is that you actually fire the fuel and control the firing based on the coil outlet temperature, that is the temperature of the fluid coming out of the furnace. Now, the fluid coming into the furnace the temperature can vary. So the feed coming into the furnace, its temperature can vary. Now, if the temperature goes up of the feed coming into the furnace, obviously the firing has to come down because now there is more heat with the feed coming in. So, for example, if suppose the feed coming in is at 280 degrees Celsius and it has to come out at 360, this is typically what we do in the atmospheric crude unit in refineries. The crude comes in at about 260 to 280 degrees Celsius, and then it is heated to 360 in the furnace. Now, what happens is that if suppose we have feed coming in at rather than 260, it is coming at 280. Now, obviously, by the time the PID controller takes action, there would be high skin tube temperatures of the tubes, and that would reduce the life of the tubes in terms of the metallurgy. So what one can do is that there's a 20-degree rise in the temperature in the feed coming in. We can actually negate the value of that to that extent, and therefore, reduce the amount of firing into the process, into that furnace, because of the higher temperature of the feed, and vice versa. Okay, so this is a good example to talk about the heater inlet temperature changes. And mathematically, how do you do that? We actually, the disturbance variable, the value, and you put it through a lead lag block. because it's not only the gain, but also the time variation, which is extremely important. And let me tell you how to do that. So basically, this lead lag block is nothing but a transfer function. So like when you teach process control, generally you teach process control in terms of Laplace domain. So this actually compensates both for the transportation lag and a first order lag. And so we have three parameters here: gain, time constant, and dead time. Let me explain actually. I don't think this needs real explanation, but just this particular case tells you how to calculate that. And why I'm spending more time here is because this is a very essential component of multivariable advanced control. So let's say you are taking cooling cold water at 30 degree, and you're heating it in a vessel which has steam coils inside, and the hot water comes out at 60, and the steam flow is 200 kg per hour. At a certain time, if you increase the steam flow to 230 kg per hour, that means there is more heating now available in this pool of water. So the water going in actually will get heated up more. So the same temperature water will get heated up to, let's say, 68 degrees Celsius at steady state. So when you actually make a step change from 200 to 230, this hot water temperature will go up and slowly and steady out to a 68. So when it reaches a steady state, the final value of this temperature, that is 68 minus the original, upon 230 minus 200, which is the change in the steam flow, is the gain of the process. Okay. The second is what is the time constant. So the time constant is nothing but the process hold up, that is the volume of this vessel upon the flow through this vessel. So basically in this case it is 17 minutes. So this is nothing but your first order time constant. And the dead time is the amount of time it actually takes to register the change. So it is the transportation lag, and this is the length of the pipe upon the velocity of the fluid. So ultimately, what you do is that this is the time axis and this is the process variable. With the example that I showed here, this is the time axis and this is the temperature of the outlet water. And at this point, and this is the steam flow. Right. So at this temperature, you make a step change of steam flow from 200 to 230 kg per hour. And this is the temperature of the outlet water. And it takes some time, although the step change was done here, it takes some time for that water to register an increase in temperature. And it will go through an S curve and it will come to a new steady state. So this particular delta, the difference between the new steady state and the old steady state, is the gain. The point of inflection, that means the point at which this curve has the maximum slope, is the if you draw a tangent on that point, and that the point at which it intersects the x-axis, that distance from t is equal to 0. This is t is equal to 0. So from t is equal to 0 to this point is the transportation lag, that is theta, and the tau is actually nothing but the time constant from the intersection from the x-axis to the point of inflection. And as you know that if you want to represent this particular response in Laplace domain, it is nothing but the response upon the input data, that is y upon x. In Laplace, yx upon xs is equal to e to the power minus tau, that is the theta, e to the power minus theta s into gain upon 1 plus tau s. So this is a kind of a representation in Laplace domain, and you can always take the Laplace inverse to get it into the time domain, which is not difficult. So this is actually what is called as process identification. And this is a very important component of advanced control. The more accurately you can model the process, that means you can identify these three constants, the more actually accurate you would be in terms of your control. And remember, I mean, although we are modeling this lead, so this is the lead lag block. This is this is Kp into e to the minus theta s upon 1 plus tau s. And beyond that, the third advanced regulatory control is what is called as the inferential control. If you remember, I mentioned one of the limitations of advanced control is one of the limitations of regulatory control is that the control variable should be measurable. Now, what happens if the control variable cannot be measured? If the control variable cannot be measured, we need to calculate it. And the good news is that it is really possible. A lot of such variables can be actually inferred and calculated from the operating conditions by applying the general theory of chemical engineering, that is heat and mass balance. And these variables can be divided into two categories. One is the engineering variables, the other is the product quality. So product quality like compositions or vapor pressure and things like that, and engineering vapor variables like flooding in a distillation column, heat duty, horsepower, and so on and so forth. The examples are given at the bottom. So I'll just give you an example from our refinery. For example, naphtha, if I want to actually know what is the 95% boiling point of naphtha, naphtha is actually a gasoline component which you actually buy from the petrol station. It is one of the important components in petrol. And if I want to know at what temperature 95% of the naphtha boils off, that can be calculated. And so what we do is we actually calculate this by direct online measurement using the variables like pressure and temperature. And this gives you a fairly good comparison. This is the 95% point. The black data is the lab data, and the red data is what we predicted. And you can see that it's not too bad in terms of the red and black kind of following each other. So to a very large extent in our refineries, we do this, and once in a while we check the accuracy of this prediction by lab data, and we do a kind of a self-adaptive tuning. Now, having actually discussed advanced regulatory control, now let me come to what to discuss multivariable model predictive control. This will now become very easy for you to understand. This is the state of the art, and then let me tell you why we want to discuss advanced regulatory control. Although conventional advanced control is good, it is easy to understand. All applications can be done within DCS. People have to just understand the background process, and the implementation time can be extremely short. And good news is that it can be done in stages. You can do nonlinear, and then at some stage you can do feed forward. And believe me, I mean, I've done a lot of these implementations myself, sitting on the panel by taking the operator in confidence. And when it works, even these small, simple things, the kind of happiness and the pride that you get out of it with a happy face of the operator is worth remembering. So this is something that I would suggest the faculty to take initiative and do it in the chemical and small plants that we have around in Mumbai and Vapi and Gujarat area. The limitations is that it is still difficult to handle process interactions. So you still have one algorithm per loop. It's still difficult to handle constraints, and we are still not optimizing. In other words, we are still not trying to make real money because we are still trying to stabilize the plant operation. So that brings us to the state of the art in advanced regulatory control, what is called as a multivariable model predictive control. And it can do everything excepting to boil milk. It can handle all the difficult control problems, whether it is an inverse response, there is a time delay, you have several loops interacting, you have limit constraints on both manipulated variable, control variable, and more importantly, it can handle a non-square system. So for people who actually have not actually been exposed to multivariable model predictive control, they will not perhaps understand what is a non-square system. But let me tell you what is inverse response. Actually, let's say, for example, in a boiler, in the water vessel, which is feeding water to a boiler, when you actually increase the steam flow out of that boiler, the level should go down. But actually, it doesn't happen. When you actually increase the steam flow from a water boiler, actually the level will go up, and after a while the level comes down. The reason is that when you draw more steam from the boiler, actually there is more steam bubbles which are formed, which actually occupies the space in the water pool, and thereby actually gives a higher level. And once those bubbles burst through the water liquid level and go into the steam flow out, the level subsides, and then actually you bring more water in to make up the level. So that is what is called inverse response, and I'll define what is non-square system in a moment. But before I do that, I'd like to introduce some definitions. There are four definitions around any control system that you can think of. We have already talked about what is manipulated variable and a controlled variable. Manipulated variable is something which you actually change in the process, which is like a control valve, or a control variable which you want to control at a set point. But there are two more variables which actually have to be defined when we talk about multivariable process control, and that is disturbance variable and constraint variable. Disturbance variable is something which you can measure, which actually affects the process. In terms of what I introduced to you when I was discussing a feed-forward control. Disturbance variables which you cannot control, I don't think you need to worry about, because the feedback loop of the PID controller will take action. Something like ambient air temperature and ambient humidity, etc. I mean, if you're smart enough, you can even feed forward that as well. But this could be actually considered as unknown disturbances. But the constraint variable is a process output which need not be actually controlled at a set point, but within a limit or a zone. So let's say horsepower. We don't actually control the horsepower of a motor at a certain value. As long as it doesn't exceed 450 horsepower and it doesn't go below 300 horsepower, we are fine, you know. So that is the kind of a constraint variable. So if you remember this, we already talked about MV and CV, but if you remember DV and CV, then we can actually define what is multivariable control. Just to tell you, you know, like when I mentioned about multivariable interactions, this is a very simple example which will tell you how two loops interact. Actually, this is a simple distillation column, and you have reflux, which is actually controlling the overhead temperature here, and the reboiler, the reboiler, which controls this temperature. Now, what happens is that if you actually increase the reflux, it may not even change this temperature, but it can change this temperature as well because more liquid comes down. And similarly, if you put more steam through this reboiler, it will change T2 for sure, but it will change T1 as well. So both reflux as well as the vapor boil up do have an impact on the two temperatures that we want to control. And superimposed on that is the change in the feed flow and the change in the feed composition. So this is actually could be a known disturbance. And if you don't have an online analyzer, this could be an unknown disturbance. All right. And the flooding in this distillation column could be something which is a constraint variable, which you would like to limit between two limits. So going from there, actually, this particular diagram explains what I actually mean by multivariable model predictive control. Believe me, you don't need more than this one diagram to understand what is multivariable model predictive control. So let's say in this case, same distillation column that we are looking at. So there are three manipulated variables. One is the reflux. The second is the steam flow in the reboiler. The third is if there's a partial condenser at the top, the control valve opening on that partial condenser. And the control variable is the overhead temperature. The second control variable is the bottom temperature, and the third control variable is the column pressure. And there's a disturbance variable like in terms of feed flow. So what we need to do is that in the actual plant in this distillation column, we have to first of all assume that each one of these four variables, the MV1, MV2, MV3, and DV1, they actually affect all the three control variables. So we actually take one at a time. So we actually do a step test on MV1 and develop the relationship between the change in MV1 with CV1, CV2, and CV3. And this is the same relationship that I mentioned earlier. That is the gain with the dead time and a single order response. That is e to the power minus theta s into k upon 1 plus tau s. So there are three parameters which are linked with each one of these lines, you know. So MV1 so you got CV1 upon a CMV1, CV2 upon CMV1, and so on and so forth. So if you can count, there are 4 parameters on this side, 3 parameters here. So there are 12 interactions. So you have 12 different models. So you can imagine now, you can actually understand and appreciate what I was saying, that the manpower effort is humongous here. And during that test, the pump might fail. There could be a thunderstorm. Some disturbance might happen, and then you might have to call off that test and then redo it again next day. So each one of these tests could even take 2 or 3 days before you get a good response, and then you have to do it one at a time. So in a big process, you could have many manipulated variables and you could have many control variables. What I mean by constraint variables is, in multivariable advanced control, the definition of control variable disappears. In other words, no variable, whether it is pressure or temperature or level or flow, is controlled at a set point. It is always controlled within certain limit. So for example, if I'm controlling the overhead temperature of the distillation column, and I'm trying to control it at, let's say, 82.5. Now, there is nothing sacrosanct about controlling it exactly at 82.5. There could be changes in the column pressure. There could be suddenly a kind of a snowstorm or a hailstorm, and the outside temperature might come down, and you might have a fin fan cooler, so the cooling duty will go up, etc., etc. So what is required is what is done in multivariable advanced control is that we control the variable within a certain limit. So the overhead temperature, instead of being controlled at 82.5, we control it between, let's say, 81 to 83 or 80 to 85, like that. And similarly, the bottom temperature and the pressure. And even you could have other constraint variables like flooding, where we'd like to actually make sure that the column doesn't go below 60%, it doesn't go below above 75% flooding. Flooding can be calculated based on AICHE correlations, etc., which you teach in the classes. And similarly, the horsepower of the pump, etc., they can all be calculated and displayed to the operator and can be part of this multivariable function. Now, this is actually a square system where you have 3 manipulated variables and 3 controlled variables. Now, it could happen that since each of these variables are no longer controlled variables, these are constrained variables, because they are being controlled in a certain limit, there can be 2 situations. One situation is that you could have more manipulated variables as compared to controlled variables. In other words, one of the controlled variable actually comes and sits on the upper limit. The other comes and sits on the lower limit. And actually, they have to be now controlled on those limits. Okay. And in such a case, if suppose one of the manipulated variable, let's say the reflux rate, the control valve goes fully open, then you are left with only 2 variables and 3 variables to be controlled, because all these 3 are sitting on their limit. So this is a non-square system where you have 3 controlled variables and 2 manipulated variables. And this is actually, as you know, is an indeterminate system, because the degrees of freedom is now -1. And therefore, actually, there is a gradual degradation of the control system that we do. And then what we do is we try to say that, okay, which variable which variable we can allow to go beyond the limit and it is safe. Safety is, of course, the most important aspect in any plant. Money comes next, okay? So we actually try to, so this is where the discussion happens with the CTS and operations team to define which variable we can actually allow to violate the constraint. And we do that, and then actually control the rest of the variables. And then since the process is dynamic over a period of time, we might actually get the third variable also under control. The situation can happen the other way around also. Like for example, all the 3 variables are within the low and the high limit. That means both the top temperature, the bottom temperature, and the pressure, they are actually sitting very pretty between the low and the high limit. But we have 3 manipulated variables at our disposal. Now, this is actually degrees of freedom plus 3, where we have 3 manipulated variables and we have nothing to control. Now, this situation actually leads you to now optimize the operation. So what would you do actually? Which is more important? Now, the top product, if it is more important, I would like to minimize, try to reduce the reflux so that actually I bring the composition near to its constraint. So these kind of, this kind of intelligence is actually then built into the controller because now we have an opportunity, since none of the variables are being controlled at their set point, but they are being controlled in a certain bandwidth. So this, my friends, I mean, I don't think I have to get into the nitty-gritty of what is multivariable, I mean, how you actually program the whole thing, but this whole thing is available in a form of a software, very much like your Aspen or any other application software that you buy. So if you have any flow sheeting software in your college, you would very much appreciate that the software is just a piece of software. Actually, it is the people. If you have to simulate a distillation column, you have to use your domain knowledge to actually tell it how many strays and what is the reflux and what variable to fix and what not to fix and so on and so forth. So that is actually what I'm trying to explain, how to program that multivariable control. So the implementation methodology is very simple. You make a list of all the controlled variables, manipulated variables, and disturbance variables in your entire process, and then actually take one MV at a time and do a step testing. And then based on that, you record the changes in the CV value. That is what is called as a deviation variable from the set point. And you collect this data on 1 minute average data, because you'll get one data in every 250 milliseconds. So you take 4 data points and take a 1 minute average. And that you can do from the what is called as a data historian from your DCS. And that dump, you can take it on your Excel spreadsheet. And then using the Excel data fitting routine, you can estimate these 3 parameters, that is the K, the theta, and the tau. It is as simple as that. And it is, I mean, if you look at the real life problem, this is actually not exactly a full problem. This is a typical glimpse of a crude distillation column multivariable controller, where you have something like 29 controlled variables, which is including constrained variables and manipulated variables. And this is actually a pretty docile example. In fact, in our implementation, you could run into something like 100 manipulated variables with 300 controlled variables. And you can see that these graphs that you see is the process response curves. And you'll see a lot of blanks here also, because that shows that manipulated variable 3 had no effect on control variable 1 or 2 or 3 or 4. So there'll be a lot of sparsity in this matrix. And obviously, because some variable may not affect anything else. So you could even have, let's say, you would never have actually a kind of a blank row. A manipulated variable, if it is there, it would be affecting something, of course. And but this is the matrix which you actually take a transpose of. And so if you call this X, then you take X transpose X inverse X transpose, and then multiply that by the deviation between the PV value and the set point, and you got your controller. Okay. So delta MV, which is the vector, is equal to X transpose X inverse X transpose of that deviation variable. And the X is nothing but this matrix, which is nothing but your theta e to the power minus theta s into gain upon 1 plus tau s. So all these graphs are actually approximated that way. So the benefits of advanced control is that there are 2 types of benefits. So one is which is very easy to quantify. Because of advanced control, you can increase capacities, that is throughput and yields. You can have higher operating efficiencies. You could improve product quality and consistency. Obviously and definitely, you will reduce energy and smoother response to operational changes. So tomorrow, actually, if you get a different crude in your refinery, having advanced control will very slowly shift the operation from one crude to the other. There are other types of benefits which are very difficult to quantify, but nonetheless, they are there, and we call them as intangible benefits. They are increased safety. Advanced control gives you much higher safety because now actually it takes care of your metallurgy, and the safety issues are inbuilt into the algorithm that I mentioned earlier. Reduced emissions because actually it is less energy consumption. Greater flexibility of operation, better insights into the process. The operator now can talk in terms of horsepower of the pump and flooding in a distillation column rather than the delta P across the distillation column. And this has actually become the base for the management information system. And then beyond that, it's much easy to actually go for a digital twin Today we talk about digital twins, so it's very easy to actually graduate to integrate a digital twin of the process and to make it work. And you have, in general, a much more work efficient environment where actually the operator doesn't have to worry about not going to the washroom just because he feels that in those 5 minutes the process may go out of hand. So this is so. I mean, but those benefits which are easy to quantify, I'll tell you how to actually estimate these benefits. I'll end up in the next 5 to 6 minutes, but this is a very important piece because this actually gives you a kind of a satisfying feeling of how to estimate benefits due to advanced control, and more importantly, even before implementing advanced control. And it goes with the premise that actually before advanced control, you had a large variation across the set point, around the set point, and after advanced control, these variations go down. So in other words, the standard deviation of your PV value around the set point was large, and after that it reduces, which actually helps you to move the average much closer to the specification or limit. Let me give you an example. In our refineries, like in your kitchen, you use LPG. Now, the liquid petroleum gas that you use is actually a mixture of propane and butane and C3, C4. Inevitably, there is some amount of C5 which can also get in because ultimately you're separating LPG from naphtha. And the lightest component in naphtha is C5. So some amount of C5 will go in. And so if this is the C5 specification limit in LPG, and let's say this is, let's say, 1%. Now, what happens is that the way the operator operates the naphtha stabilizer, which is actually a debutanizer, which separates LPG from naphtha, you might actually violate the LPG spec a couple of times, but it doesn't matter because the entire LPG goes and gets stored in a bullet or a Horton sphere, and then it gets kind of mixed together because there's a big difference here. So he's averaging it around 0.4, 0.5% C5 content, but once in a while it might hit 1%. But once you actually reduce the standard deviation, you can shift the average up. In other words, now you can control the C5 content to roughly at about 0.8, 0.9%. And therefore, actually, you can bring more of butane, which was otherwise slipping into naphtha. We can bring more of butane to the top and therefore make more LPG. And in many public sector refineries, LPG pricing is higher as compared to naphtha, and therefore you can make more money. So this is actually the fundamentals of calculating advanced control benefits. Two aspects here. One is to what extent we can reduce the standard deviation before and after advanced control. And after reducing the deviation, to what extent we can move the average. So there are two concepts involved for calculating the benefit. The first is actually, so how do you determine the new operating point? There are various methods called method A, B, and C. A is the best operator method. B is the same percentage violation. What I actually like and we have practiced in the industry is same percent violation of the 5% limit. And I'll talk about it in a moment. But before I do that, let me tell you that this is the standard observation that we see in terms of reductions in standard deviation. You remember I mentioned that we have to believe that the standard deviation in the process variable, in this case the C5 content in the LPG, will reduce after implementing advanced control. To what extent can it reduce? Because remember, we have still not implemented advanced control. But these are the industry standards. Like if you're trying to control Caro flashpoint, the standard deviation is reduced by 60%, and so on and so forth. These are the typical industry averages. And next slide also goes on, and roughly about 60%. So a good industry number to be taken to estimate a reduction in standard deviation is by 60%. And you can never go wrong with that. Okay, so let's say if the standard deviation before advanced control was 2.8, you can reduce it by 60%. So if it is 3, reduced by 60%, so it is 1.2, all right, after advanced control. And how much can you move? It is very well given in this graph. This is actually a normal distribution function, if you may recall from your statistics background. And generally, if you sample large number of samples and determine the C5 content, so what is plotted on the x-axis is the process variable. That is the variable which you want to control. So in this case, in our LPG case, it is C5 content, and what we have is number of samples. So if you actually plot that number of samples versus the C5 content, you will find that it has a very broad distribution because the standard deviation is high. And those of you who would still remember your statistics background, 95% of the area under this graph is covered by, average plus minus 3 sigma. Now, this is the limit. That is that 1% limit on the C5 content. Okay. So these many samples, so the area under the curve after the limit, these many samples actually failed the LPG spec. But these many samples did pass, okay? So when this kind of LPG mixes with this LPG in the hot sphere or bullet, it meets the overall spec anyway. But because actually we kept the average, that is the average of the C5 content, the set point, at very low as compared to the limit. After advanced control, after 60% reduction in standard deviation, obviously the probability, the normal distribution function becomes more peaked. In other words, the standard deviation goes down. And therefore, by assuming that 5% of the samples still actually, violate the LPG spec of 1%, because it was working like that for 30 years plus. So why can't it work now? Right. So what happens now that this is the new area under the graph after advanced control. And that area after advanced control is equal to the previous area before advanced control. And in order to make these two areas equal, we can now shift the average towards the limit. And that's what we actually meant here when we said that we can shift from 0.5 to, let's say, 0.8 or 0.85%. And we still don't, violate the limit. So this is how actually you calculate. So let's say if I shift from 0.5 to 0.8 or 0.95, and I can do a simulation on Aspen to understand how much of more LPG will I make. And the way to do it is by reducing the reflux to the distillation column, and then how much less naphtha we will make. And so the difference in the pricing between the LPG and naphtha into the total production of LPG per hour into 8,000 or 8,200 hours in a year. That is the money that you make by actually putting this advanced control. And these are the typical numbers. Since I told you that I'm from a refinery background, so these are the various unit operations that we have in refinery: crude, vacuum, FCC, reformer, hydrocracker, alkylation, delayed coker. And in our Jamnagar refinery, we have all of them, excepting the hydrocracker, the light ends, the isomerization, lubes, etc. You can see the amount of benefits that you can make per barrel. Okay. And the maximum is from the crude because the entire crude barrel comes into the crude unit. And so these are the typical benefits that you make a year, which is quite significant, But in addition to that, the intangible part is that it makes people and processes safe. And more importantly, it keeps the equipment safe. It gives you higher reliability, more efficiency, and a long-term sustainability. And in addition to that, of course, it makes money. So that's it I had to talk to you about. And if you have any questions, please do let me know.
Yes, sir. Thank you for your informative presentation. I'll just see the questions. Sir, many more appreciations from our participants. Very interesting session, informative presentation, sir. One question is from Chandra Kumar Mohor.
I can't hear you. Can you speak a bit louder? I don't know. Let me actually see if I can increase the volume here. Yeah, my volume was a bit low. Yeah, tell me.
Yes, sir. Many more appreciation came from our participants.
Yeah, can you repeat?
Many more appreciations have come from our participants that informative presentations, sir. Very interesting session. Now
Thank
one
you.
question is coming from Chandrakumar Mohor. How logic controller and transducer was in controlling process parameters?
See, what happens is that when you have a full control loop going from the plant to the control room and back, it starts with the pressure with the measuring element. So whether it is a pressure, temperature, level, or flow, what happens is that you have to put a transmitter. So let's say you have if you're measuring the flow, so the hardware is the orifice plate, and the orifice plate you measure the delta P across that orifice plate, and then you take the square root of the delta P. That square root of the delta P signal from that orifice plate is then taken into a transducer, and the transducer actually sends a signal 4 to 20 in the range of 4 to 20 milliamp to the control room, where the PID controller takes that value as a process variable, compares it with the set point, and the output goes also as a 4 to 20 milliamp signal. Now that signal goes into a transducer, which actually converts that from a pneumatic air, from an electronic signal to a pneumatic air signal, and that pneumatic air then works. That pneumatic air then works on the drum of the control valve to make it open or close. So that's how actually technically it works. So the last piece at the end of the journey is always pneumatic air, because the control valves do operate only on pneumatic air. And this is what we call as an instrument air in our plants.
Okay, sir. Then another question from Sanjay Bhagat. Sir, how can we apply advanced control in agriculture-based raw material process which have many uncertainty?
But in other words, to make the agriculture raw material like pesticides or insecticides.
So it is not mentioned, sir. Sir, just only he mentioned agriculture-based raw material process.
Yeah, actually, if you look at agriculture raw material, there are two major categories of agriculture raw material. One is the fertilizer, the other is the insecticide or pesticide. Fertilizers, of course, they come from large complexes, like Rashtriya Chemical Fertilizer, or from, FACT, and so on and so forth. While actually the pesticides are made by, there are also reasonably big companies like Hindustan Insecticides Limited, or by multinationals. And in fact, I would say that it's more important to actually apply advanced control there, because a lot of these reactions which we do to make pesticides and insecticides are quite dangerous reactions. And it's very important to actually control these processes using advanced control, because otherwise you can even set up runaway reactions here. So, I mean, I would need to have a specific example to actually give you a specific answer.
Okay, sir. Next question is Milin survey. What challenges can we face for periodic and non-periodic calibration of such systems?
Challenges for periodic and non-periodic?
Calibrations.
Oh, okay. No, I think it's a very good question. Actually, this still remains a challenge with some of the most advanced companies also. But the success of advanced control can only be as good as the instrumentation. Let me put it this way. So if your instrumentation goes bad, there is no signal coming in. So what do you control, right? Now there are two things which can happen with the instrumentation. Either it is completely off, which is good in a way, because at least the operator knows that it is out of order, and he can then actually place an order to either replace it or repair it. But the bad news is, and the worst part is that the instrument works, but it is erroneous. And there also, actually, the worst part is if there's a gross error in that data. That means there's a delta. In other words, the temperature it shows is always 85 or 84, 83, but actually it should have been 120. At least in many instances, I've seen some temperatures which I never understood. And when I asked the operator, तो वो बोला कि साहब ये 85 दिखाता है, मगर आप इसमें 30 डिग्री ऐड कर दो, तो ये 115 ही है. So this is something that is very dangerous. And if you try to put advanced control on 85, you can imagine what can go wrong. So instrumentation is a very important part, and the greatness of advanced control is that because advanced control can succeed only if the instrumentation is good. So actually, just to make advanced control successful, the instrumentation repair and maintenance also goes up. So this is actually one of the intangible benefits that you get by implementing advanced control, that the instrumentation people are on their foot, trying to maintain the instrumentation all the time. Otherwise, it will show up and advanced control will go out of order, and the management will ask, "Bhai, kya ho gaya? Advanced control kyun nahi chal raha?" So I thank you for this question. Instrumentation is the important aspect in advanced control.
Yes, sir. The next question is Dr. A.R. Lokhande from LIT Nagpur. What is PLC used in solvent extraction plant?
Sorry, what is?
PLC used in solvent extraction plant.
That is a very general question. Solvent extraction plant could consist of either a liquid extraction column. Maybe Lokhande knows me, my background about solvent extraction, I guess, is from LIT, it's the same college as mine. But no, I don't understand. PLC stands for Programmable Logic Controllers. And Programmable Logic Controllers is a new name for SLPC, that is the single loop programmable controllers. So basically, that's where the PID sits in. And in solvent extraction, the one thing that you would definitely do in a PLC is to control the solvent to feed ratio. So whatever is the feed coming into an extraction column, you would like to control the solvent based on the feed rate. So the feed varies, the solvent should vary too in the same proportion, and that is the critical part in solvent extraction. Rest raffinate and extract will come out. Generally, these extraction columns operate under pressure, and if the solvent is the dispersed phase, the interface will be at the bottom. So you actually measure the interface and control the bottom flow out. That means you manipulate the bottom flow out by controlling the in order to control the interface at the bottom, and the top is either a decant, or if the column is operating under pressure, then the raffinate is withdrawn under pressure control. So these are the three control systems that you implement around an extraction column: a feed flow control, the solvent to feed ratio control, the top raffinate on pressure control, and the bottom liquid under interface level control.
Yes, sir. Sir, and myself, Dr. Atibari, I have a question. Sir, how the inverse response compensator is implemented in the boiler? You have given the example in boiler.
Yeah, no, actually what happens, Aarti, is that in the typical boiler, there is no way we can implement inverse response control. See, what we do is that there is a level controller on the drum, on the water drum, and if suppose the level goes down, we bring in more water, okay, from the outlet. So there is a flow control on the water which is cascaded onto the level control, but that controller can actually get confused if you suddenly reduce the pressure in the boiler to draw more steam. And when you draw more steam, the bubbles get formed. It actually increases the level. And if you draw more steam, because more water is converting to steam, the level should come down, and therefore it should bring more water. So also actually when you bring more water, if you don't have a recuperator in a boiler and the water is coming cold, it actually collapses the bubbles too. So although the water is coming in, the level still goes down. And that again further confuses the controller. So inverse response can only be handled by a multivariable control. And even in this boiler, if you do actually step testing and model this in terms of that e to the power minus theta s upon 1 plus tau s into kp, you can actually model the inverse response as well.
Yes, in software we can model.
Yeah.
Sir, I have another, just I want to know, is there any example of split range control applied in industry?
Example of?
Split range control that is coming under multivariable control.
Yes, there are plenty. I'm so happy you mentioned it. Actually, we do it all the time. See, whenever you do, I'll give you a good example which you can teach the students too.
Yes.
See, for example, I'll have to give a long answer, maybe 2 minutes it will take, if it's okay with Professor Kole. See, I'll tell you what, people, when they teach process control, I think it's very important to teach the students how to control the pressure of a distillation column. Okay,
Yes, sir.
and this is a pet question asked in the interviews. Okay,
Hmm.
in fact, if you wish, I can help some of your students to actually prepare for these interviews, take their mock interview, etc. Because see, let me come back to this. Like, how do you control the column pressure? So suppose somebody asks you, how would you control a column pressure? The first thing that you should ask is, at what pressure is the column? Okay.
Yes.
So the column can be at three different conditions. It could be either at pressure above atmospheric, or it could be at a pressure at atmospheric pressure, or it could be under vacuum. Now, if it is actually operating under at atmospheric pressure, then how do you control the column pressure? Because it is atmospheric. So what you do is that you take the overhead vapor from the distillation column, put it into a condenser, and actually if it's a total condenser, that means all the vapors do condense. There is no uncondensables there. Then, but you still have to control that pressure, because actually there could be a rainstorm outside, or the ambient temperature might fall during winter. So how do you control the pressure? So what you do is that you bring nitrogen. So you put a nitrogen line on the overhead drum, which receives the condensate from the condenser, and you put a split range control there, what we call as a push pull system. So what you do is that if the pressure starts to fall, you bring nitrogen into that overhead drum, and if the pressure starts to go up, you actually throw out nitrogen from the through another control valve. So the outlet of that, there's a pipe which connects from the overhead drum, which actually either gets connected to the nitrogen coming in, or actually nitrogen going out. So this is called as a split range control. So let's say the pressure goes, so we put a set point. Let's say the pressure goes above 1.08, then actually it will take out nitrogen from the system. If it goes below 1.02, then it actually brings nitrogen from the pipe, from the nitrogen supply system. So this is called split range control. So between 1.02 and 1.08, no action is taken.
Yes. Okay, sir. Thank you.
This is the simplest example I could do. I can give you, but there are other examples also in the industry where actually, if suppose a flow has to be controlled, and there is a range of flow, then actually, let's say the range of flow is, let's say, 100 to 2000 meter cube per hour. I'm just giving a very hypothetical example. Let's say 400 to 2000 meter cube per hour, and therefore actually the flow is on two pipes. There's a small orifice plate and there's a larger orifice plate. So the controller actually takes action in terms of controlling the flow based on the small orifice plate when the flows are small, and based on the large orifice plate when the flows are large. So that is also called as a split range control.
Yes, sir. Thank you, sir.
You're
Now
welcome.
okay. Now over to Dr. Nitin Kole.
Okay, thank you, madam. Respected sir, we are much obliged to you for gracing your expertise and giving an excellent coverage to basics of advanced process control used in industry. Sir, the talk was really very much beneficial to our all participants. I, on behalf of entire organizing team, extends a very hearty word of thanks to you for accepting our invitation and guiding us in this faculty development program. Thank you very much, sir.
You're welcome.
Thank you very much, sir.
Thank you.
Now I request our director, madam, Dr. Geeta Latkar, to say a few words. Please, madam.
Yes, good evening, one and all.
Good evening.
I'm glad to extend our thanks from bottom of heart to Mr. Garg. Sir, it was a very interesting and great lecture that I heard. I don't belong to your fraternity, actually. I am a mechanical engineer, but
Okay.
I found it quite interesting, and I'm happy to have listened to the session as such.
You're
Um,
welcome.
uh, Actually, it is said that Vinoba Bhave has said it. You may be knowing his name.
Oh yeah,
He was a
I'm from
great
Nagpur. I'm
educationist.
from Nagpur.
Yes, and he said that the river in the book doesn't make you drown, or the boat in the book also doesn't help you to get out if you are
Yeah.
drawn. Okay. So the we teachers, we are deprived of the industrial experience as such, so we are deprived of the practical exposure. And if we share, I think, like with you guys, I mean, the people from industry, if they come forward and participate in the education process, like some such thing that has happened today, so I think that will make our teaching enriched, and that will give our students more exposure through you. I understand that you cannot be that much available, but if the training the trainer is done by the industry people, I think we can better transfer this experience
Yes,
to
sir.
students. And I'm very much thankful to you for having come forward and spared your time for our teachers.
Thank you.
Yeah, thank you very much, sir.
Thank
And
you. You're
you are
welcome.
again welcome when this lockdown opens. You are welcome to our institution
I
to
will come. I'll
share
definitely.
your thoughts with our students.
Yeah.
Our Director General, sir, is also here. So, like, I will not be taking much of time as such. Um, Only then expressing thankfulness towards today's speaker. And I am thankful to all the participants who have made this program successful. I learned it that there are more than 100 participants were there for this program. There are 8 engineering colleges in the vicinity, but I think this response is quite good. And if these many teachers are trained, I am sure that you will be reaching to like the students minimum 50 times the number of participants in this program.
Yeah.
So thank you very much, sir.
You're welcome. Thank you.
Uh, Thank you, madam. Now I would like to invite the participants to share their views regarding this FDP, overall FDP. Please, you can raise your hand so that we can unmute you. Dear participants, yes,
Hello.
yes, sir.
Very good evening to all. On behalf of the participants, I wish to extend our heartiest greetings to yourself, that is Dr. Kole, and all the team, and our compliments to management of MGM for supporting this endeavor. Right from planning to execution, everything went very well. All the speakers invited were stalwarts in their field, and I think the today's session delivered by Honorable Garg sir uh, has given us a very good impression about how a thorough and studious industry authority can be. It was a very well demonstration about how to present the topic, and the in-depth knowledge and the way of presentation was a lesson for all the teachers. On behalf of all the participants, I would like to compliment Garg sir that even though we are a trained teachers, but even though you are from a industry, you have taught us or demonstrated how the topics can be presented very effectively. And one more take home message for all the participants from your today's session, that humanware is more important than hardware, software, and the other. So we'll definitely take take back this message and implement in our day-to-day academic practice. Thank you once again. Congratulations to the organizing team for organizing very well FDP. Thank you, sir.
Thank you very much, Professor Praveen Bhandari, for your kind words. Thank you. Is fine. Okay. नहीं है ना? Now I would like to request our director, Madam, once again for her closing remark of this FDP.
No, I think I have done with my job, and I request Director General Sir to say a few words. Before that, I would like to thank our management, our chairman for being encouraging for organizing all these activities. And I congratulate Dr. Nitin Kole and his department for having organized this program. Okay, and thank you all the participants once again. I request Director General Sir for his concluding remark.
Thank you.
Good afternoon to you all.
Good afternoon, sir.
It's my privilege to be part of this valedictory function. Honorable Chairman, as Madam has mentioned, is encouraging all such activities, providing all the facilities, and that's the reason every week we are getting industry experts to our college under the departmental slots or other activities, including guidance to the quick learners. And that's an advantage being in Mumbai. And we are extremely grateful to all the industry stalwarts, academicians from higher educational institutes and research organizations to help us in helping our students and faculty by the regular visits to MGMCET. And that has become some sort of a culture in MGM College of Engineering. And this is one of the activities in continuation of that culture. And today's feedback, although it is only one person, Mr. Bhandari has given the feedback, but it's like Shitavarna Bhatachi Pariksha. So I'm sure all the participants have been benefited by such lectures by experts from industry, experts from academic institutes, including IIT, ICT, and research organizations. One gets a multi-dimensional picture about what's going on, what is the latest, and what way the technology is moving. And this helps our faculty to keep abreast with the latest developments in the technology. I'm sure such activities, which are normally conducted in our college every semester, go a long way in helping the students and the faculty to enrich themselves and bring the academia from higher education institutes, research organizations, and industry close to our college. And that's the greatest benefit we get from these close interactions. I could be part of the sessions. Today I heard Mr. Gerd talking about the industrial automation and instrumentation. And that is what we have to learn, that how this entire thing takes place in the industry. And I'm sure such lectures, now that these lectures are available on YouTube, will go a long way to help our students and faculty. I congratulate the organizers, particularly Mr. Nitin Kole and his team, the entire team which has done this activity, for their continuous efforts in bringing in the experts, as well as conducting these sessions very carefully so that it benefits a large number of participants. I was told that more than 100 participants have attended this particular FDP. Congratulations. In fact, when we talk about such activities, it is not one-time affair. It's a continuous effect of these activities which will go a long way. I'm sure as Mr. Garg is here today, I request on behalf of our management to be part of our institute, keep visiting physically so that our students and faculty get encouraged by your presence.
No, I'll do. As soon as the lockout is over, the first thing I'll do is to visit. So you're not very far. I am in Cooper Carene only.
Yeah, very close, in fact. That's the advantage of Navi Mumbai.
Yes.
Thank you, sir. Thank you very much.
You're welcome.
So, in fact, I am very much happy with this conference, which has been organized by Chemical Engineering Department under the leadership of Dr. Nitin Kole. And I'm sure such activities will continue, and it will give us an opportunity to invite stalwarts like you. In fact, I want to tell you that there are also activities which go on in our college, like projects which are given to our quick learners. And I'm sure, sir, we will definitely be part of that in guiding our students in learning something beyond the syllabus, beyond the textbooks, which will help them to compete with other students who come to the industry. And that will also make them industry ready when they come for the selection process. That is what is our purpose. In fact, I don't want to take a long time because already it's 5-6 days FDP is now concluding. I'll end up my remarks with a shloka from Bhagavad Gita, chapter 4 and verse 39. It says, Shraddhavan labhate jnanam. Shraddhavan labhate jnanam tatparasayatendriyam. Jnanam labdha parashantim achirenati gacchati. What it means is, those whose faith is deep and who have practiced controlling their mind and senses attain knowledge. So knowledge is not that easy to attain. And through such transcendental knowledge, they quickly attain everlasting supreme peace. Take care. Defeat Corona. Be happy. Thank you.
Thank you.
Thank you very much, sir, for your continuous guidance and inspiration, and having these kind words in this FDP. Thank you very much, sir.
Thank you.
Thank you.
Once again, thank you very much to Garg, sir.
You're welcome, boss. Thank you.
Thank you, sir.
Pleasure is mine. Thank you.
Now, Aarti madam, over to you. Aarti madam.
Hello, sir. A very good evening, one and all. Myself, Dr. Aarti Barik, on behalf of Chemical Engineering Department, MGMCET, would be privileged to extend my heartfelt gratitude to our Honorable Chairman, sir, respected Director General, sir, and respected Director, Madam, for their encouragement, motivation, and support to conduct this 5 days online faculty development program. With their immense support only, we could successfully finish this program. I would like to extend my sincere gratitude to all our speakers on this FDP who are prominent professors and scientists from world-renowned institutes and industries for their invaluable contribution by gracing this platform, sharing their valuable time, knowledge, and experience with us and our participants. They all put their efforts to enlighten us by the ongoing innovative research and advanced technologies for upgrading environment by utilizing waste to create energy and troubleshooting in industries. Rather, I would like to mention their individual names here. Heartfelt thanks to Dr. Preeti Subedar, Associate Industry Technology Specialist in Novozymes South Asia Private Limited, Bangalore. Dr. Pankaj Patil, Lead Engineer, Chemical Engineering and Science in Suez Water Technology and Solutions, Private Limited, Bangalore. Dr. Nilesh Gandhi, Assistant Vice President with Reliance Industries Limited. Dr. Madhukar Garg, President, Refining and Petrochem R&D, Reliance Industries Limited. Dr. Paragar Gopte, Professor in Chemical Engineering Department, ICT Mumbai. Dr. Rahul Bhosle, Associate Professor in Chemical Engineering Department, Qatar University, Doha. Dr. Sanjay Mahajani, Professor in Chemical Engineering in IIT Bombay. Dr. Sunil Vazir, Deputy General Manager, UPL Limited, Ankleshwar, Gujarat. Dr. C.S. Mathpati, Associate Professor in Chemical Engineering in ICT Mumbai. Dr. Avanti Saw, Professor in Chemical Engineering Department in NIT, Rourkela. I extend my sincere thanks to our HOD sir, Dr. Nitin Kole, the convener of this faculty development program, for his continuous motivation, guidance, and involvement in grand success of this program. My genuine thanks to our Dr. Chemistry sir, co-convener of this FDP, for his effort, involvement, and cooperation. I extend a very hearty thanks to all our organizing committee members, Dr. A.R. Lokhande, Professor Nishan Saule, Professor Umakant Khandalkar, Professor Prajakta Angre, Professor Yogesh Karpe, and Dr. Rajashree Javle, because of whom this function was made possible. Thanks to all the faculty and staff of MGMCET for their direct or indirect support for grand success of this FDP. Last but not the least, I extend my sincere thanks to all our participants for attending this online faculty development program and taking part sincerely in question answer interactions with the speakers. Thanks again. Thanks a lot to all.
Thank you.
Thank you, ma'am. Thank you.
Everyone, please stay safe. Take care of yourself.
Thank you.
Thank you.
Thank you, madam. Thank you, sir.
Right.